All right, so last night, while I was preparing this talk, I realized I signed up for something really bad. It's like 15 minutes, and I have to go over like running Kubernetes on Amazon, which some of you who have tried, it's not a greatest thing to do and cannot be explained in 15 minutes. So I changed my topic to just generalize it like a smart person. So I changed it to Kubernetes, and we'll talk about some of the Amazon stuff that Hootsuite did and our journey towards setting up a production-grade cluster. But we'll mostly like kind of open it up for new people that are in this meetup. I saw a bunch of new people kind of sign up. So it'll be a good introduction into Kubernetes. So we'll go through the fundamentals and go forward from there, basically. So my name is Mishra. I work with these two guys, Mark and Luke. We kind of work on the scheduler and so on. And Luke actually stole the show with like the best talk in the front. So we go from like, actually showing you the result to how we actually went there and how we built it. So I'll start with a show of hands. So just to kind of grasp like where everyone's coming from, how many people actually have used Kubernetes and kind of worked with it and so on? Cool, awesome. How many people use Amazon to run their workloads? Not running Kubernetes, but run their workloads. It's a lot of people, okay. How many people want to run Kubernetes on Amazon? Well, my advice is don't do it. That's my advice, to be honest. Like, don't do it. Don't do it. You can avoid it. Don't do it. I'm just joking. OK, so we'll go through some fundamentals, then go through the architecture, and then go through our deployment of Amazon and how we got into it, and then some other options that are available. All right, so start with fundamentals, and this is important. I'm just going to go over pods and nodes, because these are the ones that are relevant to my talk. But you can see other primitives online on kubernetes.io. You can go through them. It's very well explained. So pods are basically the most fundamental unit in Kubernetes. You can kind of see them, look at them as VMs. So each one of them has an IP. And then each pod can have multiple containers or a single container. In our case, we usually go with a single container. But all the other containers that are inside a pod, they feel that they're part of the same machine. So they kind of share the resources such as CPU, memory, and network, and so on. And the best part about this model is that each pod gets an IP. So you have kind of a flat network. So you can have one pod communicating with other pods directly using the IP, which is nice. Then nodes, it's another important piece to this puzzle. Node is the actual physical server or virtual server, I guess, in Amazon that runs these workloads. So it can run like multiple pods and depends on how many pods you assign to it, basically. All right, so we'll dive into the architecture. So 8 months ago, when we started researching on, but 4 months, we've been working on this for 4 months. 8 months ago, when we started our research, we were already running Mesos, and we kind of knew the internals and so on. We were really into like the code and how it actually works. So we wanted to do the same thing with Kubernetes. So I started like researching on it, like usual person, like you'd go to blog posts and read some papers and then go on. And then do some Google search and so on. So what I actually found, I was super confused. Like, this thing is like not well explained anywhere. I wasn't happy with the explanation, like even on the Kubernetes side. Then what that made me realize is like there's got to be like someone who's actually explaining it like in a very simplified form and which is very sane. So I looked through Kelsey Hightower. He works at Google. He's a developer advocate there. So he actually did a really good YouTube video explaining this, and it resonated with me. So I wanted to use that kind of. I got his permission, by the way. So I want to use that to kind of like explain you guys what's going on here. So I think the most important part in Kubernetes, and I feel the way you can learn it is using and learning the API. API is like the key and kind of the gateway into Kubernetes. It is understanding all the objects that are stored in the API, which is really important. So let's say now you have to run some workload, run some applications. That's when the kubelet comes in. So kubelet is something that actually runs your workloads for you, and it attaches itself to the API and listens to the events there. Now, you can actually fairly like do basically make a Kubernetes cluster work, but then you might have to schedule your workload yourself. So you might have to say, hey, run this pod on this node and so on. But Kubernetes actually comes with a scheduler. So by default, it has the scheduler does bin packing. So it basically distributes the workload based on the bin packing algorithm. And then the other core component is something called the controller manager. So this is something that basically makes sure that whatever you define in your APIs, your pods, and your deployments, and so on, they are implemented across the cluster, and they basically watches for control loops and make sure that everything is basically running as expected. Then there's something called kubeproxy, which I kind of feel it's like a training wheel for Kubernetes. It's kind of like it eases your adoption of the platform. So it lets you kind of like access your services, applications inside the cluster, which is, I think, really useful and really important. And then something called kubedns. kubedns is basically a DNS service that runs inside Kubernetes. It kind of exposes that service discovery thing that Luke was talking about onto your application. So basically, the idea is that you don't have to change your application to make it work with Kubernetes. If you're already using DNS, might as well use it. And it kind of ties to that. Then you have the only stateful component in this whole thing, which is etcd, which basically stores all the distributed system crap inside and keeps it out. And then your runtime. So this could be Docker, Rocket, or so on. But what I feel like runtime is actually a really small part of the whole thing. It kind of disappears once we start using it a little bit more. The more you use Kubernetes, it just feels like a computer, which is nice. And like the more you kind of forget about all the crazy architecture stuff and like the internals that's happening in the background. For you, it's like more like a computer. You use all the primitives that Kubernetes has to offer, the pod primitives and so on. And it's really nice. And that's one of the reasons why we started using it. OK, so our journey began. This is 4 months ago, as Luke said. We started off with something that Kelsey put out, which is Kubernetes the hard way. This is basically a guide that goes through. It's open source, of course. It goes through like setting up a Kubernetes cluster in Amazon, but it doesn't use any automation tools. So it doesn't use like Terraform, and let's say it doesn't use Ansible or Chef or so on. So you actually do everything from ground up, which is nice because it gives you an experience of what it takes to run a Kubernetes cluster and what limitations that Amazon has, basically. So we went through this, and this is what it gives you. So it's a simple deployment. In this, you have 3 instances, 3 Amazon statically scaled instances, 3 nodes that are running, like basically running EC2, and then you have the core components, API server, controller, manager, scheduler running in the master, and even etcd in this case, because I guess that's how we thought about implementing this. And then you have an ELB to access the Kubernetes API. And then the kubelet also listens to the API server, basically. So it's pretty straightforward. Now, the first thing we did is like, OK, let's run some workload on it. So how does pod-to-pod communication work? Basically, that's where the question came. So how does like pod 1 wants to talk to pod 2, for example? So how does that work? So here's where I hope everyone can see this. Here's where I'll introduce a few things, which I don't want to go in depth because I just have 15 minutes. But what I'll talk about is like something simple, some simple deployment, I guess, simple example. So in this case, you have something called a cluster CIDR or IP range. So it's something, a group, like you basically tell Kubernetes is like, when a pod comes up, since every pod has an IP, just use this IP range and give one IP to that pod, basically. So you tell Kubernetes, like in this case, we've said /16 or whatever. So each node actually gets assigned a /24 range, a set of IPs, basically. So as soon as one pod comes up, each one gets one IP, basically, in this case, as you can see. And then, of course, these are Amazon instances, so they have Amazon IPs as well, right? Now, how does communication work in Amazon? You use the routing table, and it's all good. And this is what exactly the tutorial goes through. So basically, you set up node 1, node 2 in this case. It has like those CIDR blocks that I was talking about assigned to it. And now, basically, we have the whole routing set up. So now, pod 1, when it wants to talk to pod 4, it can go through the Amazon routing table, come in, and this should just work. First time we tried it, did not work. And I was like, why is this not working? There's something called source destination checks, which I've worked with Amazon a lot, like for 4 or 5 years, and I'd never like heard of these guys. So source destination checks is basically, in Amazon, it's like the way of protecting their network in a way that if the instance doesn't see its source IP in the source of the packet and the destination, it just drops the packet. So in this example, if you see like the IP range that we're using is like an internal like IP range, 192 range. So it'll just say, oh, this is not a traffic that I expect, and your VPC is actually defined 10 dot whatever. So I'm just going to drop it. So once you turn it off, it works, which was nice. So the first time we finally got like everything working, which is awesome. We kind of experienced this kind of communication problem really early on, which is nice because that exposes us to some of the limitations that Amazon has. So once you add an instance, add a node, all you have to do is add another routing table in Amazon, and you're good to go. You can start routing. Make sure the source destination check is off on that, and you're good. So what is the advantages of this? Basically, one of the advantages is that you're using layer 3 and you're using Amazon routing table. It's all good. You're using a cloud provider for doing the right thing. And then it's a simpler implementation of this whole thing. But the limitations is actually something that one of the reasons why we didn't go with something like this is there's a max in Amazon for 50 routing table entries. You can ask them to increase it to 100, but they'll say, OK. And then after 75, you start seeing some performance issues as well, like once you have 75 entries in there. And I think I've heard after 80 or something, it starts skipping like these lookups for some reason. I don't know, some weird issues with that. So we didn't go with this kind of this setup. And then there's some complex orchestration involved in which, when a node comes up, you have to make sure, the routing table entries are in there. But now I think the new versions of Kubernetes actually supports all this orchestration. So if you want a smaller cluster, this is fine, this is great. You can actually implement this and it'll work, and you don't add any complexity. So our production criteria was pretty straightforward. We wanted each cluster to have at least 1,000 nodes. We have thousands of servers in Amazon. We use Amazon really heavily. So you want to make sure that each cluster is kind of independently support that scale. Then it should, of course, has to be ops friendly. We were a team that's kind of separate from ops then, and we want to make sure when we are done with this thing, it all works as expected. We are on call for that, by the way, for the whole cluster. And then, of course, it has to be highly available because I have to use this keyword. That's why I put it in there. Second, then there's it has to be easily reproducible. So basically, let's say we go multi-region or whatever, and we want a cluster in Ireland. We should be able to do that and have multiple cluster per environment, so per use case for some reason. And then make it secure. That's one of the other things, because this is going to be our microservices platform. We want to make sure that it's secure. So I'll just talk about few because I don't have the time. So I'll just talk about the few of these high-level decisions and how we kind of went about these. The first one was increasing that scale. Like if you recall from the last slides, there's a limit on the routing table. Can we just not use the routing table? And you end up using the routing table for routing the actual packet. But can we not use it? And how can we do that, basically? So can a pod directly talk to another pod without doing that lookup and having that orchestration kind of done? So what if you could actually wrap the packet around a UDP packet and say, and put an Amazon IP on there. So basically, the node that's actually making the call can do the wrapping and so on. So that's where the OLA networks come in. I'm not going to talk about OLA networks. People can give hours and hours of talks basically on just the OLA networks, and I'm probably not the best candidate for this. But I'll just talk about what we did. So we ended up using Flannel. Basically, Flannel is an OLA network in which what we ended up doing is basically just use VXLAN. So in this case, what happens is, let's say pod 4 wants to talk back to pod 1. And so the destination packet will have the IP address of this pod. So what Flannel does, Flannel D that's running on both nodes, what Flannel does is basically wraps that packet and puts the UDP destination to be the node, which is node 1 in this case, and that's it. And then this packet is routed by Amazon. It thinks it's an Amazon packet. It comes in and then gets routed to node 1. And then here, Flannel kind of unwraps that packet and routes and says the destination to be this pod, and then that's all done. So one important thing to note here is one of the few reasons we were trying to stay away from OLA networks is it just makes things complicated. Like devs already have to deal with so much, and then you have to, if there's some production outage, and God forbid it's something to do with networking, it'll be hard to debug, of course. And the other reasons, there were many reasons why we didn't want it, but ended up we had to do it in order to reach that scale, unfortunately. And the other thing is we use Flannel in something, we use a flag in Flannel called subnet manager. So basically in that case, what happens is we use Kubernetes as the source of truth for how these subnets are allocated per node. So Flannel handles all that. So Flannel basically handles the startup of the pod, assigning it a IP and so on, which is nice. All right, so that works for us, and this is what we are running now. All right, so let's move on to the reproducible part and making it secure. Again, I have 15 minutes, so I'm going to try to do the best here. Okay, so we love HashiCorp tools at Hootsuite. We pretty much use every one of them except Nomad, of course, because we chose Kubernetes. They were really choked about that. And this is our pipeline to get through Kubernetes. So I'll go through the important pieces, and we'll eventually blog about this. So I will go through every detail. Don't worry about it. It's going to be named Kubernetes the really hard way, and we'll post this for sure. There's going to be a series of blog posts. Just you can count my word on it. So we start with basically Ansible. Ansible is what we use for our config management at Hootsuite. So the good part is you don't have to do much scripting for Kubernetes stuff. It's all Golang. It's nice. You get binaries. You can just run them, which is really nice. So basically use Ansible to write some simple scripts, and then it goes through the build pipeline. We use Packer there. So Packer is a image creation tool by HashiCorp that lets you export images like VMware or Amazon images or Google Computer images and so on. So basically Packer builds that AMI and then pushes to S3, let's say, and then that's where we bless the AMI. So basically we use something called Vault. Vault is another important thing. I'll talk about it in the next few slides, but it's basically the secret store that stores secrets for for your data center, for example. And then we use that to kind of like give that AMI a certain set of policies and so on. And then it goes through the deployment phase. So here's where we use Terraform. Terraform is like pretty much like the core of our infrastructure now. We use it across the board. We try to use it as much as possible. It is a tool. It is an infrastructure as code tool. It lets you codify your infrastructure, go through a plan phase, and get some code reviews done, and do some Amazon API calls basically in the back end. And the good thing about it, it's not tied to Amazon. You can use Google. You can use the Google Cloud provider. You can use the Azure Cloud provider. So it's kind of it's good that you have multi-tenancy there. So yeah, that's one of the reasons why we didn't choose CloudFormation, because we wanted to be multi-cloud eventually. So the output, what comes out of there is basically a bunch of Amazon resources, so auto-scaling groups, DNS names, and elastic load balancers, and so on. All right, so I'm going to drill into two of these things because I think they're important. As I said, Terraform is the infrastructure as code tool. You can look it up. HashiCorp has HashiCorp Vault, which is the security tool. So this is how our Terraform project looks like. It's pretty straightforward. There's not much like stuff going on there. Like in terms of like, well, I can't introduce Terraform, but basically I can't show you the files. But what these are basically, they're very simple files. So the controller is just an auto-scaling group with some bunch of DNS entries, right? ELB is basically a simple Amazon ELB that points to the controller and the APIs. And then the etcd is just a simple etcd auto-scaling group deployment. Same with workers as well. So the interesting part here is the environment. So basically, we use TF-var files, which is just the variables to supply to a Terraform config. So what we can do is we can write like one config, which is just like these set of files that can kind of get compiled to one thing. But we can use the TF-var files as a variables file and then inject environment into it. So basically, we can say, hey, deploy this in production, deploy this in staging, create like, let's say we have another deployment in, let's say, West 1 region of Amazon. We can say production West 1 or so on. So we can inject those like runtime kind of variables in it, which gives us a lot of flexibility. So that has saved us a lot of time, and this is why we have a push button kind of deploy for our Kubernetes clusters. One other thing we really worked hard on, and I think we probably spent more time. We shouldn't have spent this much time on this, but we did. So basically, we use Vault, as I said. So basically what Vault does for us is something really interesting. We use Jenkins to trigger that build, as I said from the previous slides. We use Packer to kind of build those images, and Jenkins triggers that Packer build. And once these AMIs come out, we bless them with certain policies. So in Vault, basically what you can say is you can give certain server images, certain set of policies, so they can access some secrets. So this kind of solves the chicken and egg situation for us. So, and then in Vault, there's something called the EC2 backend, auth backend. So what that lets you do is basically use the Amazon EC2 metadata. So you just use a combination of PKS7 and AMI ID to kind of say that the server, when it comes up, it says, hey, I'm a legit server. I was provisioned by Amazon. And once it says that to Vault, Vault can give it a token. So this token is actually mounted on boot. So as soon as the service loads, the first thing it does is basically do this login. And as soon as you're logged in, you have a token. It's valid for, I think, 8 days, and we can rotate it as we want. Once you log in, you can actually request certs. So each and every component in our Kubernetes cluster a request for certs, and then generates it dynamically when it comes up, and then bootstraps the whole Kubernetes cluster, basically. So every component, like the workers do that, the controllers do it, and so on. And when we have to rotate this, we just scale the auto-scaling group and scale it out, basically. And that way, we can rotate these certs, basically. So yeah, so this is 4 months of 3 of us kind of working on this, and then what we actually ended up with was pretty simple, I think, in the end. What we got is something simple. So we have 3 things here. They're all auto-scaling groups. So the controller is also running an auto-scaling group. The nodes are running an auto-scaling group. The number can go up or down based on the workload we want to run. The good thing is you can add like different types of classes of instances and then join them in the same cluster. Then you can kind of do like, like these instances are more compute bound. These instances are more basically memory bound and so on. So you can do that division with just using Kubernetes. So these instances come up and they register and so on. And then we have the stateful part, actually. We just I think we just finished it, which is also running an auto-scaling group. So that kind of initially was just statically scaled, but it's also running an auto-scaling group. And we'll talk about our challenges probably in the blog post about like what it takes to make this an auto-scaling group and make it all like run as you expect it to, basically. Then we have these 2 elastic load balancers. One's an external load balancer, one's an internal load balancer. There's a reason why there's 2. The external one is to basically access from the office for operators and so on. They can actually access the Kubernetes API using that. And the internal one is for exposing the internal Kubernetes components. So like the kubelet for the kubelet for all these nodes kind of accesses the internal load balancer. All right, so we realized after a really, really long time kind of realizing that the community is actually shifting beneath us. So there's like the huge Kubernetes community, they came up with something called KOps. And a lot of people asked us, like, or cops or whatever they call it. They came up with this tool, which is super awesome and supported by the community, which lets you do production-grade clusters with really, like, with ease, basically. So with just using this one like command, I can like create a cluster and then manage multiple clusters really easily. And there were reasons why we couldn't use it, because we wanted to do all these like custom vault stuff. And so we ended up not using it, which is unfortunate. But I think we will in the future kind of look on. And we do use it for some of our just like free-for-all like small cluster that we run in Amazon. We do use KOps, and it's super awesome. So I recommend if you have to start today, I would definitely recommend using KOps or COPS. I think Tavis was saying that he uses Kube AWS, which is another thing that I guess Unbounce is using, which is nice. So yeah, that's in the community, so you can use that. And it lets you do like create, upgrade, and delete with really ease. You can do rolling deployments, especially the upgrade that recently happened from Kubernetes 1.5 to Kubernetes 1.6, which was a painful upgrade. That was done really well by KOps as well. And then you can basically manage multiple clusters if you want to. And then the best part out of this is actually export Terraform and recently export CloudFormation as well. So you can, if you don't want to use KOps to set this all up, you can export Terraform and then run, plan, and apply, and you're good. And you have everything like kind of codified in a way. So in the end, I want to end with, again, you can see a theme. Kelsey's everywhere. Kelsey's helped us throughout this process. He's been super open, even though we were running it in Amazon and not on Google. He was super supportive with all this. So basically, this is, you can see the date. It's 11th December 2016. We started working on Kubernetes like October or something. And when I messaged him, DM'd him saying, hey, we actually have a cluster running. We used overlay. We didn't want to use it, but ended up using overlay, and so on. And then he said, yeah, like to get Kubernetes to run anywhere, you must be willing to do anything, which is true. We tried everything, and finally got this cluster up and running. So it wasn't that easy. That's it. That's the end of my talk. Yeah, we're hiring. Thanks for listening. Thanks for staying with us in this nice day today.